John started his education at the MIT, where he received his bachelor and his master's degrees in electrical engineering and computer science. He then moved to Caltech, where he received a Ph.D. in computation and neural systems. He then did his postdoc at Harvard Medical School and joined the research faculty there in the Department of Neurosurgery with his laboratory at Massachusetts General Hospital. He will talk to us today about really exciting new results, which have to do with thalamic visual prosthesis. And in addition to this talk that we're looking forward to, I have to mention that he and Nicholas Hatzopoulos have been the main organizers of the Ariadne conference that many of you have attended. It takes place every 2 years in Santorini, and it's a really nice and high quality neuroscience conference. So thank you, John, for coming, and welcome to Greek.
Thank you, Yota, and thank you for the invitation to come and speak. It's really quite nice. I love coming to Greece, being a Greek-American background. So today I'm going to talk to you about the work that happens in my laboratory. I'm going to review work that I started as a postdoc at Harvard Medical School and have continued on in my laboratory, and will look to the future as well. We're trying to restore sight to the blind. That's the whole idea. The problem we're trying to address is blindness. In the leading causes of blindness, the eyes are no longer sensitive to light, and the leading causes are diseases of the eye, such as glaucoma, macular degeneration, and retinitis pigmentosa. Also importantly, there are a number of cases of trauma, of traumatic blindness, where both eyes have been damaged beyond repair. This especially happens to the warfighter who is exposed to explosive ordnance, but also importantly to children in post-conflict areas where landmines have been laid and they happen upon them and suffer damage. In fact, in certain areas of the world, post-conflict areas such as Cambodia, it's the fourth leading cause of blindness. In these cases, the eyes are no longer sensitive to light, but the remainder of the visual system is largely intact. In glaucoma, we see some cases of atrophy in earlier stages, but largely the rest of the visual system is intact. So it's a very easy question to ask that maybe we could take the output of a digital sensor, a camera, process those signals appropriately, and inject them into the visual stream one stage past the eye, and provide restoration of function. The eye is very much like a camera. Maybe we can build a silicon-based one. That's fundamentally the idea behind the visual prosthesis. There's an image, a set of glasses with a camera built into them that communicates wirelessly to an implanted stimulator. In our case, we put that stimulator in the middle of the brain, and I'll show you a little bit more about that in a bit, and we provide restoration of function. I want to be very clear about one thing here. I am not, and no one in this field is talking about restoring the sight the way everyone here more or less sees. We're talking about restoring sight to people who are profoundly blind. They see nothing. And we're talking about providing a restoration of function which is crude at best. But something is better than nothing in this case. As a quick review, the early visual system of the human looks like this. This is a ventral view of the human brain. Light enters the system through the optics of the eye and falls upon the retina, which acts as an imaging surface, transducing the photons to electrical signals that pass down through the chiasm, the optic nerve, the optic tract, to the lateral nuclei, and then on through the optic radiation to the primary visual cortex, and then beyond to the additional visual cortices. Any of those areas that I just mentioned are valid targets for placing stimulating electrodes in creating a visual prosthesis. And in fact, most of the work that's been done to date has been concentrated on stimulating the retina, what remaining healthy cells that exist in the retina. There are projects worldwide, a couple of them worldwide, that are looking at stimulating the optic nerve. There's our laboratory in the LGN, and there's a handful of laboratories working in the primary visual cortex. There are advantages and disadvantages to each of those approaches. I'm not going to go through the details on this slide, and if there happen to be any aficionados in the field here, these are opinions, not facts, and I'd be happy to debate any of them with you. But fundamentally, this table reduces down to 3 observations. The first is that the eyes are small and move about in the orbit, and therefore bioengineering is difficult. Not impossible, just difficult. The second is the LGN is in the middle of the head, so surgical access is hard, but the unrelated field of deep brain stimulation, and I'll have a little bit more to say about that, has opened up easy, regular, and safe clinical access to that part of the brain. In fact, putting stimulating electrodes in nearby structures. And third, the brain isn't smooth. The cortex isn't smooth in humans. So that not all areas of V1, for example, primary visual cortex, are equally accessible. It just makes some of those areas harder to get to if you're putting stimulating electrodes there. Now, a bit more about DBS, deep brain stimulation. This is a completely unrelated field. It was developed to treat Parkinsonian tremor, or movement disorders like Parkinsonian tremor. I'm sure you're all familiar with Parkinsonian tremor. It is treated by putting relatively large stimulating electrodes in areas of the brain that are about 1 centimeter away from the LGN, the lateral geniculate nucleus, such as the subthalamic nucleus. And this image here is a CAT scan of a patient who has had 2 of these stimulating electrodes put in. These are actually recording electrodes, not stimulating electrodes, for pre-surgical analysis for treatment of epilepsy. But it shows you that these are routine. These bright spots here are the cuff-style stimulating electrodes, and there happens to be a tuft of microwire electrodes right here, right at the end, on the left-hand side, and none on the right-hand side. It shows you that there are various technologies that are available. These are routinely placed. There's about 100,000 people walking around worldwide with bilateral stimulating electrodes in the midbrain to treat Parkinsonian tremor and similar movement disorders. So this is an existing therapeutic strategy. We're not developing this part. We're building it. Oh, and in particular, this tuft of microwires, which isn't really visible in here, but it is definitely there, is the sort of electrode that we were going to want to use. I'll have more to say about that in a little bit. So here's a schematized view of what we want to build. A set of glasses with a little digital camera in them, communicating to an externally worn signal processor that communicates wirelessly to an implanted stimulator that in turn drives an electrode that's been placed in the lateral geniculate nucleus. Very simple idea. The devil is in the details. And there's an important fact about the visual system that I need to make sure you understand before we get into the experiments. And it's the idea that there is a map of the visual space. Now, as I'm looking onto the audience, you form all a visual scene in front of me, and of course, you see this visual scene in front of you. The spatial position of each of those bits of your visual field are very well organized. It starts in the retina. You can imagine that there's a strip of scene in front of you going left to right that gets projected onto one strip of the retina here, and those parts, and one particular point of that field projects through the optics of the eyes to one particular point on the retina. And as you were to, if you were to look across, if you were to scan across the visual field like this, you would find that the image moves along the retina because of the optics of the eye and the physics associated with that. That very clear ordering is preserved throughout much of the visual system, arguably all the visual system. But in particular, if you look at the LGN and the visual cortex, but if you look at the LGN, that map is preserved. there is a regular ordering of visual space within the area. That retinotopic map is preserved. So if we were to take that scanning that I mentioned a minute ago, say I had a laser pointer and I have to scan it across left to right while measuring the activity of a cell right at that point. What would it look like? Well, here there'd be nothing, 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 nothing. Here a lot of activity, and then nothing, 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 nothing. Because the cell only responds when light is falling directly on it. And that's what we see over here on the right-hand side. As I scan across from left to right, nothing, nothing, nothing. A lot of activity when the light falls on the cell, and then nothing, 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 nothing. That's in the reduced one-dimensional case. Of course, the visual scene is two-dimensional. Ignore the three-dimensionality for a moment. It's two-dimensional. And it looks really something like this, where each cell responds to one point in the visual scene. Now, with that background, I'm going to talk about 7 experiments. I'm going to go through details on the first 5 or so, and then we'll come to a very arresting halt because it will be future work. It's work that hasn't been done yet. And the first experiment we're going to talk about is the proof of concept. Given the ideas that I've presented so far to you, and the hypothesis that we could create a thalamic visual prosthesis, the first step is to verify that this idea has traction, that this idea has merit. So we did some experiments in a non-human primate, putting stimulating electrodes in the LGN, and watched what they did. These stimulating electrodes are very small. They are tetrodes, although they don't have to be tetrodes. In this case, we use tetrodes, which is shown here. This is one tetrode against a Nissl-stained section of cortex, not LGN, but it's still comparable. Each one of these pink blobs is a cell body, so you can see that the size of the electrodes is on order of the same scale as the cell bodies. So when we stimulate through this electrode, we are stimulating a relatively small punctate set of tissue, and therefore we hope generating a small punctate visual person. Now, you might ask, how are we going to get a monkey to tell us what it sees? It's a good question. Turns out if you put a primate, more or less any primate, into a dark room and turn on a dot of light somewhere in that room, the natural reaction is to look to it. We use that natural reaction and use operant conditioning techniques to reinforce it, so that any time we put a little dot up on a screen, the animal has been trained to look to that dot. In fact, we train them to do a little bit more. We train them to look at pairs of dots. This is the representation of the computer screen that's placed in front of the animal. Pairs of dots, one in the center, and the second somewhere in the periphery. So we put the animals, we put them in a darkened room in front of a computer monitor and measure their eye position while they perform the sequence. We present a dot right in the center, a fixation point right in the center while we measure its eye position. And they're required to foveate that. Look to that dot. Then a brief while later, we illuminate a second dot somewhere else on the screen, and they're required to look to that dot. This happens very briefly. So we watch what they do. We record their behavior. We put the dots all over the screen. Not all over the screen, we put them in different areas.
Why do
And
you just do it?
You'll see in a minute. Then every now and then, as they're doing this task, the second dot will not be presented on the screen, but we present it through electrical stimulation of the electrode that's in LGN. Now, if our hypothesis is true, that we're stimulating a small punctate, a small group of neurons, and that will create a small punctate image, or visual event, the animal should look to that. We'll see what he does. We've calibrated using this part of the system, this part of the experiment, so that we know what he's going to do in this case, and we compare it with this case here. We also do a secondary control where we don't do anything at all, and we make sure that he doesn't look to any particular point, doesn't memorize it. So we look at the results from this experiment. On the left are all of the cases for one particular experiment with one animal, 1 day's recording, where they started out looking in the center and then looked to one of the 8 dots here that were presented. The black traces are the eye position over time, and the blue dots are the endpoints of their eye motion, the saccadic eye motion. And you can see they look very consistently to one of the 8 lights, depending on where which one we choose. They're not super accurate, but they're pretty good. If instead we don't illuminate a second point on the screen, but apply electrical stimulation, in this case, the animal looks down and to the right, consistently. And so we infer that the percept that they were seeing is down and to the right. And if you look very carefully, you'll see that that point does not correspond to either of these two that are down and to the right. It's actually one that's right about there. So it's different. They're not looking to the memorized location of one of the other ones. And then in the control condition, they don't look at all, which is exactly what we want, because we don't want them to, we only want them to look when we're telling them to look. And I will show you now a movie of an animal doing that. So the blue dot is his eye position. The white dot is the dots that we present on the screen. So this is first with normal vision. Look center out like that. And now with artificial vision. The first dot is on the screen, the second one is electrical. Again, normal vision, center out, and again electrical, center on the screen, and electrical down to the right.
We don't really know exactly where the electrical stimulus is, right? You infer it from where it transits are.
So we infer it, so we do, I'm not going to talk about this, but we can actually, if you remember that I mentioned there's a map of where the visuals field is on the LGN and the other areas. So we look to measure, first before we do the stimulation, we measure what the location of the receptive fields of those cells are that we're about to stimulate. And we correlate that position with where they look. When we stimulate, we find there's a very high degree of correlation. It's comparable to the accuracy that you saw in the targets presented on the screen. And as we vary the placement of the electrode from day to day, the place where the animal looks also varies when we stimulate in correspondence.
Can you do that without damaging the LGN?
No. There's a very small amount of damage that happens every time we put an electrode in, but we do it so many times that it eventually causes damage. I've shown you proof of concept for one microelectrode generating one visual percept, tiny little punctate visual percept. In fact, I did it with 2 as well, and I won't tell you about that. The next question, as good engineers, we would ask is, well, 1 or 2 is great, but how many can we put into LGN? How big is it relative to these electrodes? If we can only put in, say, 10, we're done. There's no point. So I did a little computer-based simulation. I used a published atlas of the retinotopic map of LGN and simulated placing microwire electrodes every so many microns in 3 dimensions within the area, and then there's a simple counting experiment to see how many of them there were. And this is down here, this is a virtual serial section of the LGN based on that atlas. And the laminar structure is classic view of LGN. So what's the answer? Well, the answer is that if you're in the almost macroscopic scale of spacing, this is in microns, so every 1 millimeter in 3 dimensions down to about every ½ millimeter in 3 dimensions, you get on order of some hundreds of electrodes placed in LGN. That is, you could fit, if you could place an electrode every so many 100 microns, you could get some hundreds of them. It's not a fixed answer, of course, because we measure the spacing. So But the gist of it is that there are hundreds. 100 sounds pretty good.
What is human?
In human LGN, that's a good point. So this is monkey LGN. Monkey LGN is about 1/8 the volume of human LGN. So all of these numbers, you would multiply by a factor of 8, or these counts, you would multiply by a factor of 8 to get the equivalent count for humans. So that's very good in terms of fitting a lot of electrodes into LGN at relatively coarse spacings. Or you could look at coarser spacings even and still get a good count. Yep.
What would be the damage to the LGN if you put so many electrodes simultaneously in there?
So we don't know because we haven't done it yet. If the electrodes are extremely fine, and there are some extremely fine carbon fiber electrodes that are being developed now, the answer is probably almost nothing. With the electrodes that we were using, there would be some damage, but these people are blind. They're not going to see unless we do something. So if we had hundreds of electrodes creating hundreds of little phosphines, as they're called, points of light, what would that look like? It might look like something like this. This is a map now of, in this case, 250 contacts per hemisphere. So we're going to both LGNs. That's what the map looks like for the entirety of the visual field, which for me is about like this, 160 degrees by 120 degrees. And on the right-hand side, I've zoomed in on the central 10 degrees. 10 degrees is about the size of your fist held at arm's length, just to give you a scale. So certainly we don't have complete coverage. We do not. But it's not bad with hundreds. This is it's a total of about 500. We've also done a little analysis about which surgical approach would be ideal. I'll skip that. So what does hundreds look like? This is a little video that I made simulating artificial vision. On the left is an image of a young woman that I took with a little digital camera, just a standard video camera, or digital camera. And on the right, I put up about 500 phosphines that encode the information from that. Or not exactly the information from that. Let me stop it for a second. There's a couple things to notice here. One is that if I were to just show you this image on the right, like that, static image, my guess is that you probably wouldn't be able to recognize that that's a face. But as soon as I start the animation again, over time, and recognize that there's a person there. You might even be able to tell who this is if you knew her. You might be able to tell it was taken outside, that it's sunny, you see her raise her hands at the end like that against the sun. So that's very promising. This is with 500 phosphines. One last point. The image on the left has about 500,000 phosphines, or it's started, pixels. And on the right is 500. Even though there's 3 orders of magnitude less information, you're still able to see a reasonable amount of detail there. So that's very encouraging. But as scientists, we want to know what are the numbers. The standard way of measuring visual performance is by measuring visual acuity. And I see many, actually fewer people than I would have expected. Probably everybody's been here to the eye doctor and had their vision tested with a chart that looks something like this. Actually, we don't use this chart anymore, but everybody recognizes this chart. This is called the Snellen chart for visual acuity. We built a little setup to simulate artificial vision with a sort of virtual reality mechanism. We had our subjects put their head into a frame and measure their eye position with this video camera that you see on the right-hand side. And presented a very simple task, a true alternative forced choice task, based on the Snellen chart. What does that look like? Something like this. Very simple task. They had the screen in front of them, and a fixation point to start out each trial is presented. We measure their eye position, and they're required to look at that fixation point. A short while later, we present a black letter on white background. It's taken from the Snellen chart. They see that for 1 second, and they can look about if they want to. And then we present two alternatives in the clear. And they're required to look to the one that they think matched the cue presented. We vary the size of the letters, as you would expect from the Snellen eye chart. We also vary the number of phosphenes, the number of pixels in this simulated visual prosthesis. That combination looks something like this for the letter E. We vary the letter as well. So we go from very small letters to very big letters, and from relatively few phosphenes to a large number of phosphenes. The total phosphene count in this simulation, and this is just the central 10 degrees, remember 10 degrees is the central part of vision. Central 10 degrees here. So there's about 50 or so phosphenes here, and there's about 300 of them here. From this chart, you would expect that the combination of the most phosphenes and the biggest letter should be very easy, and that this combination of the smallest letter and the fewest phosphenes should be impossible. That was by design. We want to span both positive control to negative control. Now remember from that video I showed you a moment ago, you might think that these other cases are effectively impossible, but your brain integrates information over time so that this is in fact a lot easier than you might think based on this static image once it starts to animate. And I'll show you, in fact, what that looks like. This is a reconstruction of this experiment, slowed down substantially, I think about a factor of 4 or 5. There's the cue. This is a reconstruction, of course. And there are the two selections that the subject has to choose from. Sometimes they get it right, sometimes they get it wrong. And we allow them to look at both of them so they can compare, as you'll see happens here. So that's what it looks like. When we accumulate all of the results from that, the correct and incorrect results, we vary the letter size, and we vary the number of pixels, number of phosphenes. And we see how they do. We built it into a graph. It looks something like this. So across the horizontal axis is the size of the letter going from small to large. Of course, the vertical axis is a percentage correct that they got on the task. Because it's a true alternative task, the chance is at 50% here. And we've broken it down by the number of phosphenes in the particular simulation. So what happens? For the smallest, let's concentrate on the red path here, which is the largest number of phosphenes, densest simulation. At the smallest, negative control, they're at chance, and as the letters get bigger, they do better and better and better. As we reduce the total number of phosphenes, this curve shifts to the right, and to the right, and to the right. Just as you would expect. So, what does this mean? We can measure the effective acuity for a given design if we know how many electrodes are in the design. And we can predict, based on that, how well the phosphene pattern will work. Okay, great.
But,
Yes?
but it's a simulation study, right?
This is a simulation, right? This is using normally sighted humans with a simulation of artificial vision. Now, the reason that we did that, I'll show you in a minute, but the reason we did a very simple task like that was that we wanted to do the same thing in monkeys. And you'll see in a minute about that. But it's an extremely boring experiment. It takes 2 hours for each individual, and it puts you to sleep. Even the most motivated subject goes to sleep with this task. It's incredible. So we wanted to do something that was a little bit easier to do and more engaging. So we looked to one of the tasks of daily living, which is reading. And we sought to answer the question of whether these phosphine patterns can be used to read. Now there's a standardized, just as we use a standardized test for base our task on a standardized test for acuity, now we're going to base our task on a standardized test for reading. The standardized task is called the Minnesota Reading Test, or MN-Read. It's been translated into many languages, including Greek, it turns out. This is one you probably have not seen, although some of you might have. It's an unusual test these days. But it has been very well studied. And it's presented as a series of very simple sentences that appear in 3 lines and are presented in slowly decreasing font size. And the time to read each sentence and the accuracy that the subject reads with is measured. This time, we got rid of the frame and the goggles and so forth and bought this very advanced gaze tracker here. You can't really see it in this display, but there's a big hunk of plastic and metal down here, which is the gaze tracker, and then on top of it is this integrated display. Now, the subject doesn't have to hold their head fixed. They're much more comfortable. And we present the phosphines here. And they are, again, because we're tracking their gaze position, the phosphines are effectively stabilized on the eye. And that's an important fact that I didn't mention earlier. And this is what one of the displays looks like for the sentence that's on the screen. My father takes me to school every day in his big green car. Now, if you believe that I could really actually read that, I memorized these sentences. This is with the subject looking right here, where the laser pointer is, right at the middle of H. And you can notice that the phosphine pattern is a lot denser and a lot finer right where I'm pointing. This brings me to a more subtle point that I should have mentioned earlier. Your visual acuity varies with eccentricity. That is, wherever your gaze is pointing at any given moment as you look around, that's where you have high resolution vision. In your periphery, your vision is terrible. And it's really astonishingly terrible. We have this illusion, this profound illusion, of high resolution vision. Our vision, all told, is horrible, except right in the center part, where it's exceedingly good. And our brain does a marvelous job of fooling us into thinking that high resolution is everywhere. It's not. You can prove this to yourself when you go back to your desk, or if you happen to have printed something in front of you. It's a timetable from the subway in Athens. Take a printed piece of material. Text is usually best. Put your finger right in the middle of some paragraph. Like that. Using your finger as a guide, look at the word that you've identified and hold your eyes still on that word. Use your finger to make sure that you're holding your eyes still. And try, without moving your eyes, to read left, right, and up and down. You won't be able to. You'll be able to get maybe one word. Maybe. Our resolution is terrible, except right at the center. So it's very important that we simulate that accurately. And in particular, it's very important that that pattern of phosphines, which again is due to the map of the visual field onto the area in question, that pattern moves around as the gaze moves. So getting back to the image here, that's why the phosphines seem to be smaller and denser right here where the person is looking, because they are. And that point tracks around. You'll see that in the next movie. This is the recording of one of our subjects reading. The red circle is their gaze position. So the red circle is their measured gaze position. They don't see that. This is a reconstruction of it. And you see the phosphene pattern across the screen is, again, densest right where they're looking, and it will move about as their gaze moves about. Let me start this up again.
So you use the gaze camera to do feedback, to
In
make
real-
your phosphenes like that.
In real time, yes.
Different kinds of flowers grow by the side of the road.
Now, I bet nobody really could read that along with it.
No.
Let me play it again.
Different kinds of flowers grow by the side of the road.
Was it a little bit easier that time? Maybe.
Thank you.
So,
How much practice did this exercise?
none. So the question was, how much practice? None. This is a naive subject. All of our subjects were naive. How is that possible? Okay, you remember the big difference between the static image and the moving image in the movie that I showed you before. There's another quantum leap that happens when it's your eyes that are driving that simulation versus somebody else's eyes. We are observers to the person who's driving the simulation. If we were sitting there, if you are, I say this with high confidence because we tested a lot of subjects. If you were sitting in front of the computer and driving the simulation, you'd be able to read it in this case. In just about, this is an average subject. This is not a particularly good subject. It's because it's not your gaze. It's her gaze in this case. So, but in the static case, you might be able, I could probably convince you that this says 10. Turns out this is the easiest condition. Here I have amassed the data from all 21 subjects. It doesn't say there's 21, but there are 21 subjects. Going across here is horizontal direction is the letter size, so we went from small to large, and the response rate, the reading accuracy, so the number of words that they read correctly. In the case that you just saw, it was at the highest, and then this has been broken down by family of number of phosphenes. Highest phosphene density, which is this green curve, with the largest letters. So that case up there. Everybody does 100% in that condition. More or less. And as the letters get smaller and smaller, the accuracy drops off. We get a very similar curve to what we saw before, measuring just acuity with the single individual letters. And of course, when we reduce the number of phosphenes, this curve shifts to the right, and then again to the right. And this blue trace up here is the control condition where we present the text in the clear, just to make sure that everything's fine. And everybody did that at 100%. So we,
Do you do similar analysis for reading speed?
for reading speed, it is here. If we look at reading speed, we find this is the control condition up here, which for our cohort was about 170 something words per minute, which is normal reading when you're reading out loud like this. And for the phosphene reading, here we have the highest density pattern, the medium density pattern, low density pattern. This is about 2,000 phosphenes, about 1,000 phosphenes, about 500 phosphenes. And the condition that you saw the movie of here is at 60 words per minute. It's relatively fluid reading, as you heard. There weren't a lot of stops and rewinds and replays. She was reading relatively straightforward. If you drop down to here, It's still relatively fluid, but there are certainly some problems. And down here, it completely falls apart. That's typical of this task, and you can see the same thing happens here. As you reduce the letter size, you get to a critical point where reading just stops. I should point out as well, if you were to, we didn't track reading comprehension. For proximity, you have reading accuracy. But once the accuracy drops below about 50%, which corresponds to when reading speed also drops, there's no comprehension left. So we really want to look at fluid reading if we possibly can. What does this mean? Well, for this lowest density phosphine count, which is what we conceivably could build with today's technology, these two, I don't know how to build. I think I have some approaches on how to build them. I can't build them right now. We're not doing very well with relatively large font sizes. We need to have something bigger. Okay. Now, what about monkeys? We did that letter test. We designed that letter test in humans so that we could also do it in monkeys and do cross-species comparison. Why? Because we can't experiment putting electrodes into humans without any background at all. We have to do that in monkeys first, ethically. So we have to have a baseline to compare monkey performance against human performance so that we can extrapolate when we put electrodes into monkeys to how a prosthesis would perform in humans. So we trained monkeys to do exactly the same task. And I mean exactly the same task. And this is, we've done what I'm going to present data from one animal. We have two more animals that are in the midst of training that I won't be presenting, but the data so far follow along the same paths. This is a similar plot to what you've seen before, from small to large font size, and from chances at 50% and performance on the task. It's been broken down by family of phosphine count, going from a very sparse 125 total phosphines, it's a very sparse phosphine count, up to a very dense, twice as dense as what you showed. With monkeys, we can extend the parameters, it's much larger because we get them to work for 3, 4, 5 hours every day, just 2 hours from each individual.
And you don't fall asleep?
They don't, remarkably enough. And you can see that below about 1,000 phosphines here, this monkey is doing terribly. It's at chance. There's some increase in performance here for the 1,000 phosphine case, and it gets better for 2,000, even better for 4,000. When I saw this plot initially, I was very concerned. Because if you compare this plot to the way humans perform, it's terrible. But it does show that we train animals to recognize letters. Not just recognize letters, which is actually no big deal because monkeys, there's a 5-decade-long history of training monkeys to recognize arbitrary visual objects. Of course, they don't see them as letters the way we see letters, but they just see them as arbitrary visual objects. But it turns out monkeys don't do contour integration. I wish I'd built in one slide, but famous visual illusion. Everybody can see the triangle, right? The triangle does not exist. I did not draw a triangle. There are these breaks in the lines, here, here, and here. There's no triangle there, but everybody sees it because you're integrating this contour, or these contours, into solid lines. Monkeys don't do this. Turns out this is a learned behavior that Charles Gilbert in particular has been studying. Children don't do it either. We are trained into this as part of visual experiments. So monkeys inherently don't do this, which is why this is so bad. And it turns out it's really hard to train monkeys to do either that or this.
However, triangles onto the usual contour there. So
Right.
I have no idea whether monkeys are connected.
Trained into it.
I see.
And so we kept going. Having learned that, we continued training the animal. And here's what happened.
You
This is-
train them to that? What do they do?
We train them on our visual task. So it starts out with the same graph that you saw a minute ago, and day by day by day by day by day, continue to get better and better and better. One more time. The monkey is continuing to learn. He's learning contour integration. Okay, back to this. Here is the end case. This is after about 120 days of training, which is 4 or 5 months, something like that, all told. Again, broken down as it was before. And now I've added these squares, which are the equivalent for human performance that I showed you before. So we're comparing now naive human performance to highly trained animals, or one animal. And the short version is that for when the animal's doing well, they do about the same as monkeys, as humans. When the monkey is doing poorly, they're doing terribly, or terribly, because they haven't learned to integrate contours across larger distances. That's the working hypothesis. Okay. Now, in the last couple of minutes, the next thing we want to do, and this is where I'm going to now come to a relatively screeching halt. This is what we've done so far. The next step is to put electrodes into a monkey, or monkeys, get them to do the same task, except using real artificial vision instead of simulated artificial vision. We are about to, it's going to be a matter of weeks. I actually hoped that it would be done by now, but a matter of weeks before this is started. Once we have those results in hand, we can then look to doing the same thing in humans. We'll have solid evidence from proof of concept, from skipping forward too far. We'll have enough solid evidence that we can propose doing an initial experiment in a human volunteer. From that, we can then start talking about actual device design and implantation and doing a larger cohort, say 6 to 10 individuals. And from then on, it just becomes normal device development. It's no longer science, it becomes the stuff of industry. Okay. Let me skip through that. So to review, I talked about the proof of concept that we did in a monkey using 1 and 2 pixels of real stimulation. We're able to use those real stimuli in a visual task, and I forgot to mention there that there was no learning involved. The first time that we engaged stimulation, the animals responded correctly to that task. The first time. In both animals, there's 2 animals there. We then did an engineering validation to assess how many electrodes we can fit into LGN using some reasonable assumptions. And using reasonable assumptions, we get the answer of hundreds in monkey LGN and perhaps an order of magnitude, if we're lucky, order of magnitude more in humans. We did a simulated assessment of visual acuity in humans, and the answer was we get good performance, surprisingly good performance. We then did an assessment using reading, and again, got surprisingly good performance with the caveat I mentioned right at the end that we can't probably build those systems yet, but that we really need to. We can build something, not the really good ones yet. We then looked at doing the same assessments with monkeys. We have data from one animal and collecting data from a couple other animals. The initial results are good, but that is ongoing. And in the near future, we're going to put electrodes into an animal We're going to start with 64 electrodes. We have good confidence that will be able to get us a relatively good performance. Excuse me. And then the future, we look to implanting our first human subject. Finally, I need to thank our sponsors, the National Institutes of Health in the United States, the NEMA Foundation, the Rappaport Foundation, and the Ken Hall Charity Fund, who have all been very generous in supporting this work. And my collaborators, both at Harvard Medical School and Massachusetts General Hospital, who have helped with these experiments. And thank you for your attention.
What type of plasticity do you think the LGN might have undergone in traumatized individuals too?
So
the devices work well both in normal and pathological.
So I can't answer the question directly for traumatic damage, or there's also a small number of people who have their eyes removed for medical reasons, for cancer from the orbit, for example. We don't know. But in glaucoma, we do know. In glaucoma, the output layer of the eye, the retinal ganglion cell layer, atrophies and perishes, and that's the cause of blindness. Of course, it leads to blindness. And you see, therefore, atrophy in the optic nerve, which is the axon bundle from the ganglion cell layer. You see some atrophy in LGN and almost none in B1. There is some atrophy in LGN. It's probably, I don't know for sure if it's going to be preventative for using the device, but I don't think it will be. We won't know until we try. I suspect that there will be plenty of material, plenty of cells left to stimulate. And again, we're not talking about creating regular vision, high resolution regular vision. We're talking about creating a very crude vision that maybe, if we're lucky, will get up to the threshold of legal blindness, which is about, in that reading task that you saw, that's about the threshold of legal blindness.
Well, yeah, so the question was mostly for, how can, given that you know that there's some atrophy, is there something that you can do before to maybe counteract the atrophy?
I don't know. I don't. Yeah.
So on the curves we've seen with trained monkeys, they needed something like 4K of these photo thingies. Phosphates, yeah, to actually read. But you can put up to 400 into their brains, is that correct?
Well, it depends on how fine you can space the electrodes. So some of the electrodes that we're looking into using are 5 microns in diameter, which is extremely fine. And those cause no damage, numerical damage. If you limit yourself to 1% tissue displacement, which is what the Utah array does, the array of silicon probe bed of nails down. That occupies about 1% of the tissue that it's sampling. And if you limit yourself to that, then and I haven't done this simulation, I would expect to see thousands and thousands of electrodes fit into LGN, in monkey LGN, for the relatively fine spacing to be able to get. Now, can we get that relatively fine spacing? I don't know. There's a lot of development that needs to be done on the exact way we put electrodes, get electrodes to splay out in a way that's necessary to cover the LGN like that, especially if we use the very fine carbon fiber electrodes like that I mentioned. Without those carbon fibers, we won't get thousands. Not in monkeys. We'll get hundreds. But hundreds still, there's something here with hundreds. If we can concentrate the electrodes just into the central part of the visual field, then we effectively double, the 250 count density. If you can take the 250 electrodes, instead of spreading them around out throughout the entire visual field, just put them in the central part, then it's the equivalent to jumping up on rocket. So with 250 electrodes, you get this performance. So that helps. It's not enough. We are clearly limited by the number of electrodes that we can put into the area. And it's an engineering problem.
How long can you leave them?
We hope to make it permanent. For a vegetable device, it needs to be permanent. The DBS electrodes for Parkinson's disease are permanent. And those seem to be relatively well tolerated.
How many of those?
There are 8 contacts.
Yeah, compared to hundreds.
Right. It's a different scale. And those are questions that we need to answer. Absolutely.
Are there any experiments from other kind of prosthesis in other areas where they actually put a lot of electrodes and they stay permanently?
Just the Utah array experiments that are being done for motor prostheses, and those are relatively well tolerated. I don't know that any of those patients have had that tissue explanted yet after having a chronic implant. But they seem to be relatively well tolerated in humans. In monkeys, we know that they're very well tolerated. We have years worth of implant data and then histology. There is damage from those, but they're big in comparison. But they're well tolerated.
How do you control these electrodes? Apparently, this is just my ignorance. It seems it's been used in patients already for Parkinson's and other things to have these implants. How do you control them from outside?
So those
They have to be wireless, I guess.
those have an independent stimulator that just stimulates. It's a very simple, dumb stimulator that just sends a square wave at 200 hertz.
Which is incorporated inside the electrode.
And it's not inside, it's in it's like a pacemaker. It's implanted right here with wires that go up under the skin to bolster the skull.
So you have internal wires under the skin.
Yeah. Just like a pacemaker, heart pacemaker. And there are more advanced versions of that, which are being used for epilepsy, and I think they've been FDA approved now. But the reason I mention them is they're responsive. They have some sort of circuitry built into the stimulator that records, it senses when a seizure is about to occur to apply the stimulation to quash it. But again, those are entirely implanted. What we're talking about requires a wireless link, but those, the retinal prostheses exist now. Those are on the market, in fact, with a relatively small, 16 electrodes at present. And they work just as I've described. They have a camera, glasses, they're relatively large, and a wireless stimulator that actually is here that puts its electrodes into the retina. Surgery is crazy for that purpose. It's incredibly difficult. Surgery for a DBS implant is easy. Deep brain stimulation implant. We'll be using the same surgical technique.
What do you use?
So it's something like what we would use. It's really easy. You cut a hole, you put the electrode in. That's about it. It's considered, the entire surgery takes about an hour to treat Parkinson's disease. It takes about an hour. It's considered minimally invasive. It's done under local anesthesia. It's a very easy surgery. I'm simplifying. It's a bit more complicated, and of course it is brain surgery, but it's very straightforward. There was a question.
Yeah, we know that the LGN consists of distinct layers of paracell and nanocell.
Yes.
You have not investigated that. I mean, this is the first thing you simulate paracellular versus nanocellular, and I haven't seen anything with contrast, for example. Would contrast make a better difference compared to resolution?
So you have two important questions that you asked. One is, can we do anything with the laminar information in LGN? I'll just do a quick review. LGN is a laminar structure. Each lamina comes from one eye, one of the other eyes, and it's almost exclusive. And the upper layers are very simplified version. The upper layers are where color vision happens, and the lower layers are where luminance vision happens. That's incredibly simple. But this is a lecture on functionality. So you can imagine that if you were to put electrodes into the upper layers, you might be able to get color phosphates. And if you put them in the lower layers, you would get colorless, or just luminance phosphates. We don't know that yet, because we haven't been able to control it exactly. Well, we haven't mapped precisely where each electrode has gone yet, for non-scientific reasons. We could, we will, and it just hasn't been done. The data that I showed you before was collected without identifying precisely where each electrode was placed, and the histology was not available once they had this psychological portrait. So that data is lost. When we put the electrodes in shortly, we will do an exact mapping and an exact identification and get the histology afterwards, so that we can precisely measure the characteristics and associate them with each line. That was the first question. Second question is V1 is cortex a better spot than LGN for stimulating? That's a complicated question, or the answer is complicated. The, again, very simple version of that is, very simple answer is that the LGN, the encoding of signals at the LGN level is relatively simple still. It's almost identical to what you see with the ganglion cell layer in the right. Once you get to V1, things are very complicated. You have many more levels of information that have been integrated. And if you look at the response characteristics of each individual cell, or even a small group of cells, you now have direction sensitivity, you have phase, you have simple versus complex cells, you have color versus non-colorable. They're all mixed together, and there's no a priori way of separating those out. So it would seem that it'd be a lot harder to get a functional prosthesis in V1 than in LGN. That said, there are still people who are pursuing it, and it may be that those barriers are not really that important. It may be that once you put a stimulating electrode into V1, you get a phosphine which is just a blob. And the early indications from human work where that has been done is that's exactly what happens. You just get a blob the way you would get in LGN, or you get in the retina, we know. So maybe it's okay. Maybe my arguments against it really don't matter because that's not the way it works. That could be the case. What is the case, though, is that the important central part of the visual field, when you have high-resolution vision, is often buried in the interhemispheric fissure. It means it's a little bit harder to get to. The surgical axis requires removal of a larger part of the skull, and now we're talking real brain surgery, as opposed to, very easy brain surgery. It's much more difficult. Now, can we get around that? Maybe. I don't want to say it's impossible to refer to a conversation we were having earlier Any other questions?
So, in the one study, the first one, the process study, so if you try different products, how large these products do you use?
So I'm an engineer. I don't understand how currents activate cells or electrode. I don't understand that. I understand how voltages do. So we apply voltages, not currents. Yeah, that's not it. Anyway, 4 volts seems to be high threshold. And the current, when we measured the current, was some microns, some small number of microns, which is similar to what you see with in monkeys for cortical stimulation.
So the threshold was about using 4 volts.
Yeah, about 4 volts.
So how can you be sure? I guess, I would take it for granted that if you stimulate the agent, you will reduce it to spin. But now, looking at the results of the experiment, how can you be sure that you didn't just evoke a saccade? Because you're
Yeah, so that's a very good question, and I worried a lot about that. So I presented a very condensed version of the experiment. I studied it very carefully. I looked at the data in many different ways. The most important thing that I did, though, was a double saccade task, which I didn't talk about, where there's a central fixation point first, and then 2 points. So this appears first, and then 2 points get flashed in sequence. And the animal has to look first to the first one up here, and then second to the second one up here. When the second one is electrical, the animal's fixating here, and those two happen. The animal's still with their eyes here. If electrical stimulation is just evoking a saccade, then we would expect the animal to look like in this direction. Or to look first here and then here. But the animals looked here and then here. So probably not directly evoking the saccade. Also, we looked at the latency of the evoked saccade. And it was as you would expect. It was not, it had the latency of saccade evoked by perception rather than directly going to, for example, spherical cortex. And there are fibers that go from the LG to the spherical. It didn't go directly, it wasn't fast enough to directly do that. It was slow and had the appropriate mechanics of reactionary saccades. No, directly opposed. I worried about that a lot.
I guess I would just have the monkey releasing bars.
I have never trained an animal to do anything with their hands, and I've watched people training to do it, and it takes forever. And you need to get your data.
One way to experiment this on the today is to have a target of different contrast. And we know that contrast on optical increases the latency.
That's a good idea.
You can see the same happens.
Yeah, that's a good idea. That's a good idea. So it's very late. Yeah. But at this point, I am convinced that we're not directly evoking the saccades. Of course, the proof is going to be once we use this array of phosphines to deliver cognitive content, to recognize the pattern. Then it will be, for sure.